Okay, so we've been talking about symmetries. We've mentioned that a symmetry is a function. Now, the other big concept we've been talking about is groups. So let's try to bring all these things together. We have an operation on the symmetries, namely composition. So let's see if we can create a group from the symmetries on an object under the operation of composition. Okay, so let's look at one particular example, figure 9.5. So these list the different symmetries of a triangle. So we've represented in two different ways. Here you see the picture, how the triangle before goes to the triangle afterward. So here there's nothing happens, so we have this identity tableau. In this one, A goes to the position of B, B goes to the position of C, C goes to the position of A, so the resulting triangle is here. So A goes to B, B goes to C, C goes to A. That's a rotation. Another rotation would be if A goes to position C, B goes to position A, and A goes to position, and C goes to position B. I'm showing this as a counterclockwise rotation, as is usual, but you could also show it as a clockwise rotation. A goes to C, C goes to B, B goes to A. All right, and we get this tableau. We could also reflect about any of the three corners. For instance, suppose I take a line, an axis here, and imagine putting this axis in my finger and twirling so that C and B interchange. Okay. So that's this tableau here. A stays the same, C and B interchange. Similarly, we could use this axis and twirl here, C and A interchange, or we could use this axis, A and B interchange. Looks like these are all the symmetries. Can you think of any others? Well, let's assume that those are all of them, and we'll talk about that issue later. Now, we can display the composition of these symmetries in a table, like a multiplication table. All right. This is our notation for all of them. Identity, that's the Greek letter rho for rotation. Rho 1, rho 2, rho, and this is mu1, mu2, mu3 for these flips. Okay. Right now here, if you look at how this works, this gives the composition of any two of these symmetries. For instance, if I wanted to find mu1 rho 1, remember how we do that. We start with rho 1 because when you have mu1 composed rho 1, if you're first applying rho 1 and then you're applying mu1. So let's verify mu1 rho 1. Okay, you would take rho 1 first and then go to mu1. So that would be A goes to B. So here we have, let's just write here, mu1 rho 1. Sorry, mu1 composed rho 1 is equal to what? All right, we know we're going to have A, B, C on the top. So let's see what we get on the bottom. A goes to B, and then B goes to C. So A goes to C. Okay. Then B goes to C, and then C goes to B, so B goes to B. C goes to A, and A goes to A. All right. So what did we end up with? We ended up with one of the flips. This looks like rho 2, mu2. Okay. So we should have mu1 composed rho 1 is equal to mu2. And let's see if that works. Here's rho 1, here's mu1, and we got mu2. So that one worked. All of these can be derived in a similar way. All right, notice you've got these other facts here. You've got identities here, which is good. That's a good thing. Then what else do we see that's good? look at the first row and the first column, the identity does act as it's supposed to. The identity composed row 1 is row 1, identity composed row 2 is row 2, etc., etc. So the first row is the same as the index row, and the first column is the same as the index column, which indicates that the identity is doing its job. All right. All right, so this makes the point that when you compute the entries of the Cayley table, you start with, you're looking up F composed G. When you're looking at F composed G, but when you compute, you start with G and then do F. Hopefully the example I worked out for you illustrates what you're supposed to do. All right, so some exercises to investigate this table. And this is called a Cayley table. And you can verify by the, well, look at the table. The operation has closure. The reason it has closure is that every element in the table is one of the elements on the margin. We can also verify inverse. You see that the inverse of row 2 composed row 1 is identity. That's the same as row 1 composed row 2. And all the other ones are their own inverse. Identity is its own inverse. All of the mu's are their own inverses. All right, so it looks like we're getting there. Okay, so we have identity, we have inverse. Okay. Turns out we don't have commutative, but that's not necessary for a group. All right, so the last property we need to check is the associative property. Okay, and that actually follows because composition of functions is associative, and symmetry is a special case of composition. So we have the associative properties. So in fact, we do have that the symmetries of an equilateral triangle do form a group. Okay, so we've done this for one figure. What about in general? Can we prove that the set of symmetries of any figure form a group? Well, let's do the properties one by one. First of all, does the set of symmetries have an identity? Well, one of the symmetries is simply not moving the figure at all, and that's the identity function. And indeed, the identity function composed with any other function is going to give you that other function. So we do have an identity. That's the non-moving symmetry. Second proposition, all elements of a set F of any figure have inverses. Okay. Now, remember, symmetry is a bijection. Okay. So since it's a bijection, it's going to have a inverse, and in fact, that this function is going to be the inverse of this function S. However, we need to show that S inverse is itself a symmetry. So S inverse has to leave unchanged the distances. It has to leave the angles unchanged, and it has to leave the appearance of the figure unchanged. Okay, so let's go and do these 3 points. The proof that S inverse leaves distance unchanged, that's going to be exercise. So let's do the proof that S inverse leaves angles unchanged. Okay. So choose any 3 points in the figure and let A prime be, so let's do a figure here. Let's do a triangle. Well, let's do something more general. Let's do a square. A, B, C. And let's draw an angle like this. A, B, C. Now, if you perform some symmetry on this, maybe a rotation, then that angle is going to rotate as well. Okay, so we'd have A prime, B prime, C prime. A prime, B prime, C prime. It's not very clear. Okay. And we want to verify that in general, this resulting angle is going to be the same as this angle. So consider the 3 points, consider their inverse images, and look, S of A prime is equal to A, S of B prime equals B, S of C prime is equal to C. And we know S is a symmetry. So we get the equality backwards. The angle A prime, B prime, C prime must equal to the angle of ABC. And since we showed this for arbitrary points in the figure, that means that any angles in the figure remain unchanged under the symmetry S inverse. Okay? So we've gotten all of the properties that we need. We didn't show associative explicitly up here, but we already said that because composition of functions is associative, then any set of symmetries will be associative. Okay, so now we have a whole set of groups that we can play with. And here's some exercises to write some other Cayley tables for some other groups. All right, now let's see how much more we can generalize. We've talked about the symmetries of triangle, square, and hexagon, but what about other polygons? Okay. Other regular polygons. Regular means that they all have same sides, same angles. Okay, for instance, this, you've seen the picture of the regular hexagon. Now, there are also irregular hexagons. You could do something like this. 1, 2, 3, 4, 5, 6. Okay, it's six-sided, still six-sided figure. It's not a regular hexagon. This is regular because all the sides are equal, all the angles are equal. Okay. So let's take a general look at the symmetries of n-sided regular polygons. Okay. All right, so here we did an 8-sided one. Now, we already know that the symmetries will form a group. So the nth dihedral group is the group of symmetries of a regular n-gon. We know this by dn. Okay. So let's try to count the number of elements in dn. Think about the rotations of an n-gon. Now, we actually saw this in the chapter on complex roots of unity. I could rotate this one. I could rotate this one to the position of 2, or the position of 3, or the position of 4, or the position of 5, or 6, or 7, or 8, or I could leave it as 1. That gives me 8 total possible rotations. Okay. On the other hand, if I want to count the number of flips, whenever you flip, you sort of spin it around an axis. Now, I could spin this around this axis. Let's see what this one is. Yeah, no, that's exactly what I have here. The 2 exchanges is the 8, the 3 exchanges 7, 4 exchanges with 6. Okay. I could spin it about this axis. I could spin it about 2, 6. I could spin it about 3, 7. I could spin it about 4, 8. But I could also choose an axis like this. I could choose an axis like this and spin it around. So that means 1 and 2 would interchange, 3 and 8 would interchange, 4 and 7, 5 and 6 would interchange. So there are 4 axes through the vertices, and there are 4 axes through the edges. That gives 8 axes to reflect in, so that looks like we have 8 reflections. All right, so we had 8 rotations, 8 reflections. That makes 16. So it would seem that for a dihedral group of order n, for a dihedral group dn, there should be 2n symmetries in that group. Okay, and this discussion repeats what I just said. This characterizes the rotations in dn. Okay. And then let's see about the reflections. One interesting fact about reflections is that they form their own inverse. And you can think about that if you do if you take one of these axes and you flip, like this axis for instance, and you flip it back again, then you're going to get back to the original octagon. Now, in fact, what you can do is you can choose one flip, like the flip that I just shown, and compose that with any of the rotations. Okay, so for instance, I could take this flip. Well, let's go back to the original flip here. The flip around this axis. Now, before flipping, I could rotate, and that would seem that it would give me a different flip. So let's look at these n symmetries. S compose the identity, S compose the first rotation, all the way up to S to compose the nth minus 1th rotation. Of course, the nth rotation is just the identity again. And you can actually prove that any two of these are distinct, that these are all different reflections. These are all different symmetries, rather. Furthermore, we can show that this set of symmetries here, which is S composed any rotation, that none of these are rotations. And you're going to use some group properties to prove that. All right, so this set S, none of them are rotations, none of them are equal to each other, and there are n elements. So you have n distinct elements. Okay, so we have n rotations, we have n of these, we have 2n elements. We know that Dn has 2n elements, so we've shown that the elements of Dn can be listed in the following way. Okay, first the rotations, then S composed all the rotations. Okay. All right, so finally we have a geometrical way of characterizing all the elements in Dn. And this goes back to the rotations plus the flips around the different axes that I already mentioned. For instance, for the square, you actually have 4 flips because you can choose 1, 2, 3, 4 different axes around which to flip. Okay, and here's some exercises to go through with that. And you can do the tableaus. And this theorem formalizes the result that the dihedral group Dn contains n reflections as well as n rotations. All right. So that means every time you rotate and then do the standard reflection, that must be a different reflection. All right, so here's an algebraic way, algebraic summarization of the properties of the dihedral group. We actually call these two elements generators, R and S. Using these two elements, I can create any element of the group Dn. Given that R and S have these properties, R to the n is the identity, R is the basic rotation, so R to the n is the identity. S squared is the identity because S is a flip. And then we have this relation when you compose R and S. If you take Rp composed S for any p, that's the same as S composed Rn minus p. All right. Now, the thing that's important about this proposition is that given just these 3 conditions. Well, actually, this is more than one condition. It's actually n. It's actually n minus 1 conditions. Then I can create the Cayley table based on these conditions only. So these relations are enough to completely determine the dihedral group. I don't need any geometry. I don't need any figures. I only need these three relations, and that will give me the entire group structure. Now, these are actually called group relations. And as I said, R and S are called generators. Okay. All right, and that's the point that's made here, is that now I can compute any group operation simply using those relations. And well, here are some further topics that we're not going to talk about in the chapter. But here we've talked about plane figures. What about three-dimensional figures? Okay, so that's another area that symmetries can be applied to. Now we've talked about single figures, but you also have tilings. It turns out that there are 17 symmetry groups for tilings. These are called wallpaper groups. Very interesting. You can also have symmetry groups for crystals. They're like three-dimensional tilings. So there's a reference for crystal groups. So there's a lot to look into for symmetries of in different applications. Okay. Now this short section just makes a comment on something that seems very, very strange and wonderful, is that these groups seem to pop up, the same group seems to pop up in many, many different contexts. Okay, we had the symmetries of a square. This turns out to be the same as the group of the fourth roots of unity, which turns out, you'll see, to have well, no, I shouldn't say the symmetries of the square, the rotations of the square. Rotations of a square turn out to have the same group structure as the fourth roots of unity, multiplication of fourth roots of unity, which is the same as the integers mod 4 under addition. Okay, so you have the same mathematical structure in 4 completely different contexts. Okay. So that's just a very amazing thing. So something to think about. And the amazing thing is that such groups also pop up in physics in various places. All right, so I'll just leave you with that thought, and we'll stop the video here.